You should be familiar with the following rules of exponents. But even if you forget one of the rules, you can always reestablish that rule by taking a simpler case of the rule. In this lesson, we'll look at the rules of exponents and also look at easy ways of reestablishing each rule. We'll also have some examples and some practice problems for you. The first rule of exponents that I want to talk about is called the product rule, which looks like this. And it basically says if we have two values that we're multiplying that have the same base, that we can keep that base and add the exponents. A simple case to establish this rule could look something like this. X squared times x cubed, we can expand x squared as x times x, x cubed as x times x times x, and if we combine those as a single base, we have x to the fifth power. And if we notice then that from the beginning to the end, we added the exponents of 2 plus 3. An example of this could be something like x to the 12th times x to the 6th, in which we keep the base of x and add the exponents. The second rule that I want to talk about is called the quotient rule. It looks like this. And it says that if we have two values that have the same base, that we can combine those into a single power, a single value to an exponent, where we keep the base of b and we subtract the exponents. A simple case of this could be something like this. X to the 4th over x to the 3rd. X to the 4th can be expanded. X cubed can be expanded. Now if I cancel 3x's on top with 3x's in the bottom, I'm left with x to the 1st power, which comes from 4 minus 3 from the difference of those exponents. So that's a simple case that we can use to reestablish the rule. An example of this could be something like this. Y to the 12th over y to the 5th. If I subtract the exponents, I get y to the 7th. A third rule that I want to talk about is the power rule. It looks like this. B to the m, all raised, quantity raised to the nth power, is the same as b to the m times n, which says if we have some value with an exponent raised to another exponent, we add those exponents. A simple case of establishing this rule could look something like this. X squared, quantity raised to the 3rd power. If I expand the 3rd power, I have x squared times x squared times x squared. If I expand each of those x squareds as x times x, I have 6x's, which would be x to the 6th power. This rule is sometimes confused with the product rule, but if you know how to expand each one of those, you should be able to reestablish the rule if you get them confused. An example of this could be something like y to the 4th quantity raised to the 5th power. Raising the power to a power, multiplying, I get 4 times 5 is 20, so I have y to the 20th power. The next rule is a zero exponent rule. It looks like this. If b is not equal to 0, then that value raised to the 0 power is equal to 1. We can see this from a simpler case again, actually using the quotient rule. If I have something like x squared over x squared, using the quotient rule, I would subtract the exponents to get x to the 0. Well, any value divided by itself is equal to 1, so x to the 0 must equal 1. An example of this property could be something like y to the 11th over y to the 11th, which is equal to 1. And this is as long as the base is not equal to 0. Another property is the negative exponent rule. The negative exponent rule looks like this. If we have a negative exponent, we can rewrite the same base to the opposite sign of that exponent if we put that base in the other part of the fraction that we started with. In this case, b to the negative nth is in the numerator, but I can rewrite that as 1 over b to the positive n, where b to the positive n is in the denominator. This can also be shown with the quotient rule. A little while ago, we had a problem something like this. Let me use smaller exponents. In this problem, we've subtracted the numerator minus the denominator, or let's do that first. B to the 2 minus 5 is b to the negative third, but I also could have subtracted 5 minus 2, and because the 5 is larger than the 2, I would have more b's in the denominator. I would have 3 of those from the 5 minus 2 from the subtraction. If I expand this, and cancel out the b's, I can see that I have 1 in the numerator and b cubed in the denominator. Another rule is called the products raised to powers rule, in which I have some product, a times b, raised to a power. In that case, each base is raised to that power. Now notice I have multiplication here, not addition. I have multiplication, so it's a product of a product raised to a power. A simple case of this could be something like xy raised to the third. If I expand 3 of these, xy times xy times xy, I can see that I have x cubed and y cubed. As an example, 2x cubed to the third raised to the 4th power. In this case, we have multiplication inside. I can raise 2 to the 4th power. And I can raise x cubed to the 4th power. 2 to the 4th being 16. And when I raise a power to a power using the power rule, I would have x to the 12th. And the last rule I want to talk about is the quotient raised to a power rule, which looks a lot like the products raised to a power rule, in which I have some quotient, a over b, where b can't be 0. If that's raised to the nth power, then we could write that as a to the n over b to the n, in which each part of that fraction is raised to the nth power. A simple case could look something like this: x over y raised to the 3rd power. I can expand x over y cubed as x over y times x over y times x over y, giving me x cubed over y cubed. An example of this could be 2x over 3y quantity cubed, in which I can take, using the product and quotient rule, I have a product in the numerator. I can take 2 to the third power, x to the third power. Also carry out that product rule for the denominator, 3 to the third and y to the third. And if I simplify that, 8x cubed over 27 y cubed. Let me give you some examples to practice with. After I write down the example, pause the video, work the problem, and then come back to the video to check your answer. Here's the first problem. Negative 2x cubed y to the fourth, and that quantity is being raised to the third power. So pause the video, come back when you're finished to check your answer. To expand this, be very careful to remember, to raise the negative 1, the negative to the third power also, or the negative 2 to the third power. I could raise it like this, raising the negative 2 to the third power, x to the third power also raised to the third power, y to the fourth raised to the third power. Negative 2 raised to the third would give us negative 8. X to the ninth from raising a power to a power. Y to the 12th from raising a power to a power. So we used the product raised to a power rule, and then we also used the powers, the product rule, or I'm sorry, the power rule to raise powers to powers. Here's another example. Try this one. Okay, stop the video and come back to the video when you get the problem solved to check your answer. Once again, we're raising a product to a power, so let's take each value inside, or each base to the power of negative 3. Four to the negative 3 can be written in the denominator as 4 to the third using the negative exponent rule. If I raise this power of negative 2 to the negative third power, I get x to the positive sixth. If I simplify 4 cubed, I get x to the sixth over 64. We could have also worked that problem from the very beginning by rewriting this base of 4x to the negative second in the denominator raised to the third power, using the negative exponent rule from the beginning. If we work the problem this way, I still can take 4 to the third power and x to the negative second to the third power. I get 4 to the negative third as 64, x to the negative sixth, and then I can move x to the negative sixth to the numerator as x to the sixth. And let's look at one more problem. Negative 4xy cubed quantity squared, 3x to the negative second, y to the second, raised to the negative third. Stop the video and come back when you're finished solving the problem. Well, using the rules of exponents, I can take negative 4 and raise it to the second power, raise x to the second power, and raise y cubed to the second power. I can also raise 3 to the negative third power, x to the negative second to the negative third power, and y squared to the negative third power. Negative 4 quantity squared is positive 16. I'll leave x squared alone for now. Y cubed raised to the second power is y to the sixth. I'll move 3 to the negative third to the denominator as 3 to the third. X to the negative second raised to the negative third is x to the sixth. And y squared to the negative third is y to the negative sixth. If I simplify, I can combine the y to the negative sixth and y to the positive sixth as y to the 0 by adding those exponents. Y to the 0 being 1, so they're basically gone. I still have 16 in the numerator. I can combine x squared next to the sixth as x to the eighth. And I can simplify 3 cubed as 27. And so my simplified answer is now 16x to the 8th all over 27. Once again, these rules are good rules to remember, but if you do forget them, you can reestablish them through simpler cases.